Okay, we are doing the moments about an axis today, and we have problem 455, and the question is?
I'm having a hard time finding the RCB.
RCB.
Yeah, I mean, we have...
This result is a Cartesian vector, so you're going to do RCB cross F dotted with UAC. And is it U minus A? What's the U minus AC? What does that mean?
No,
or is that just, oh, that's your symbol for a vector?
Yeah.
Okay.
Yeah,
okay. Then you should put one under M too, probably, because that's a vector.
Yeah.
Well, no, actually, that's just a scalar magnitude. Yeah. But it wants the result as a Cartesian vector, which is something you ought to think about. Because this, you know, the triple product is a dot product, which is going to just give you a scalar. So to get the vector, you have to find you have to multiply that by UAC again.
Okay, you get vector.
Yeah.
Cartesian form. Right?
Yeah. Along the UAC axis.
Right. So right now, so we subtract B from C, right? It always has to be from like C to B, right? From the axis.
Yeah, has to be from the axis to the force, the line of action of the force. Yep. So it's 0, 0, 2. But wait, it's 0, 0.
But that's where we have. They say it has to be -2.
-2, yeah. This is -2 here. The point B is 3, 4, -2.
It's
yeah.
negative. Yeah.
Mm-hmm.
Yeah. Right.
Yeah.
Okay.
Is that your question?
Yeah, that was it.
Okay. Yeah. Yeah, you're definitely on the right track. Just make sure you do as a vector. You know, MAC is going to be a scalar times UAC.
But we get a scalar, right? This is a scalar.
Yeah, that's a scalar, but to get a vector, you're going to have to then take that result and then multiply it again by UAC. So you actually could write the whole thing as a vector is going to equal UAC times parentheses this triple product. Yeah. Yep. Question? Yeah?
That's a good plan.
Good plan. So this is number, which one is that, the second one or the first one? 13 or 14? So for 13, you've got, you're supposed to find about the x-axis. So mx will be ux dot mo, true, and mo is going to be rob cross f, yes, and ux is just I, yeah. So it's I dotted with rob cross f, yeah. And you could do that in one determinant, right? If you put on the top row the axis vector, which is 1, 0, 0, that's I. And the second row is the ROB components, and the third row is the F components.
Okay.
Right? So it's like, yeah, so you combine it all in one, it is, you know, UX, oops, dotted with ROB cross F. And there's a really smelly banana peel there. You got some fruit flies there. Maybe we could throw that in the trash or outside. Throw it over the railing. Gonna mess up the classroom. So when you're doing the triple product, that's the nice thing. With one determinant, you can do everything. And it's a little bit easier because you don't have the IJKs. You just put the UX, which is I. So that's just 1, 0, 0. And then your R vector, and then your F vector. And just do the determinant of that. And that will give you the magnitude. And then to find the result as a Cartesian vector, you've got to take it one step further and multiply it by its direction, which is what?
The unit vector of the force.
Nope.
Oh.
It's not the unit vector of the force.
Unit vector of the axis.
The unit vector of the axis that you're interested in, which is
X.
Oh.
Or I. Yeah.
So just
I mean, the unit vector is I. Yeah. So whatever you get as a result here is going to be multiplied by I, and that's a Cartesian vector of that component of the moment about the x-axis.
The only difference between having the axis be the x-axis and being like
an arbitrary axis. Yeah.
What's the difference? I guess.
What is the difference?
Yeah.
the unit vector is going to differ. The unit vector for
Right,
the
it's the
axis.
same-
It's a little more complicated. The determinant is more complicated because you don't have, like when it's along the X or Y Z, your determinant just has one. It has 2 zeros in the top row if it's along the X, Y, Z axis. So it's a really easy determinant. It's just like a 2 by 2 cross product you got to do. But when it's an arbitrary axis, the axis could have 3 components, and that means you got to do the whole thing. It's a little more, computationally a little more complicated, but the same idea.
So 1, 0, 0 is the unit vector along the x-axis.
Yeah.
Gotcha.
Yeah. And that is the unit. That is the UX, and then
Yeah.
if it's an arbitrary thing, like if you were doing it about ROA, which is what you're doing in 14, ROA is going to have 2 components, right? And 1, 0. The Z component is 0 because it's a flat,
It's not
so horizontal.
along
But it's a horizontal. No, it's just along the XY plane. It's in the XY plane. OA is in the XY plane. So it has no Z component.
This will give you a Cartesian, right? Like this cross product.
So then
This gives you, but it's not, it's a triple product. There's a cross product and a dot product combined. And so what you end up with is just a scalar, because ultimately you're doing a dot product, which only gives you a scalar.
Okay.
And you could do it, separately, do the cross product with I, J, K here, R, and F, and then dot that with, you're just going to grab the X component of that thing. Well, that's the same thing that this is going to do.
And then after that, you have to use I again.
Yeah, and then at the end, you can multiply by I. Or in this case, multiply by ROA.
Oh.
For 14.
Oh, yeah.
Any questions here for your planning?
I got a question.
Uh-huh.
Why is it that when we calculate a determinant
Yeah.
and we get a scalar value for this, because we have all scalar quantities up here that we're plugging into our triple product.
Yes.
So then why is it that we dot it with the unit vector of the axis?
You're not dotting it at that point. You're multiplying. When you take a scalar
Or sorry, not
and
dotting.
multiply it by
yeah,
a vector,
what
that's
I mean.
multiplication.
Yeah, like why are you multiplying it by that axis though?
Well, that's a very good question. And because, you could draw this out, right? You could say, well, which one are you doing, the 13 or 55, right? About the
AC.
AC axis, okay.
Yeah.
So what this is saying is, well, you've got a moment about A, perhaps, right?
Mm-hmm.
And if you look at the direction of, R, A, B, it's going that way, F is going something like that. So if you were going to do R cross F, you'd be having a vector moment at A, which is sort of pointing in this direction or something, right? Just conceptually, it's got to be in right angles to that vector and right angles to that vector.
Right, yeah. Okay.
And what we're doing is, when you're doing the triple product, you're finding, well, how much, if I was going to drop a projection line, we've done these projections over and over again, right? You drop a projection line, which means there's a orthogonal line, it's a right angle here, and it goes up to there. How much of that moment vector is oriented along this axis, right?
Okay.
And when you get it, right, you're getting just a number, because the triple product just gives you the magnitude.
Right.
And if they want the result expressed as a Cartesian vector, what's the Cartesian vector? Well, it's the magnitude times this direction, which is the axis that you're doing the moment about.
Okay. Yeah, so it really is a projection then.
Yeah.
Okay.
That's why visualization, is really super important.
Okay.
Yeah.
Cool, thanks.
Yep.
Yeah. So when we have to find the moment about the XYZ using the scalar technique, is this where we'd have to like visualize where it's pointing like out, like since we'd have like, we want to find the X first, right? So we'll do the Z and the Y like this. So we're just looking at it like down.
Yep, doing the X-axis, you've got the Z going up and the Y going to the right, and you've got 2 meters going to the right, fine there, and the F has an X, or as a Z, so you got the FZ component there and the FY, yeah. So that's all you see from that X-axis, right?
Yeah.
And these are the moment arms then, so it's just going to be, it's going to be FY times 3 and FZ times 2. That's the distance that SC is from.
So does it not make a difference that there's like a depth here that we don't even see in this?
Yeah, it doesn't make a difference. It doesn't make a difference
'cause it's
for the
aligned.
moment about the x-axis.
Yeah, okay.
Because, you know, it's really just going to get that thing cranking about the x-axis.
I got you,
Yeah,
okay.
yeah. Why the focus keeps scrolling.
So then if when we're doing like the Y, we would have that depth, but it'd be like a different, we'd just be looking at it like from the XZ. Like we'd have X and Z.
Right, when you're doing the y-axis, you got the xz axis, and again, yeah, you're just sort of doing a moment about the origin.
Right.
You know,
That's all you have to
that's
do.
essentially because at the origin, that's where the y-axis is coming out of that. Yeah.
Okay.
Yeah.
And is there like, oh yeah, okay. So you can just go to the origin. Okay.
Yeah.
Cool.
That's why, yeah, so you can kind of clarify that a little bit by saying, yeah, this is the x-axis, right?
Yeah.
At the origin, coming right at you.
Right.
So that's why it's,
Cool.
you're just doing an origin moment, yeah.
Cool. Nice.
Instead of dotting the cross product of those with the unit vector along X,
Yeah.
would be the unit vector along here,
AC, yeah.
or OA.
OA, yeah.
Okay,
OA.
okay, that's what I thought.
Yeah, so it's just basically the same thing, just the top row changes.
Okay, and then that would just be 1, 1, 0.
No, that's not a unit vector. And that's not even the right direction. So you got to find a unit vector for OA. Start with a position vector,
Okay, that's
divide
what
by
I
its
have.
magnitude.
That's what I have here.
It's not 1, 1, 0 though, is it?
Okay, I'll figure it out.
Well, wait a second. You're doing OA, right?
Oh wait, 0.
Yeah. Uh-huh. Yeah, so and again, when you're finished, whatever that is, this is just going to give you a scalar. So you got to take that result and multiply it by that unit vector one more time.